Good afternoon. Today, we're going to be doing lecture number 3 of ordinary differential equations. Today, exact differential equations. Exact differential equations. But first, let's look at a real-world application and try modeling a real-world application using differential equations. Because modeling is the principal thing when it comes to this. Not like there's any novel math here. What we want to do is use this in real-world situations like physics or chemistry. So let's say we have a valve over here. Don't actually really know how to draw a valve, so I'm going to draw this flower-shaped thing instead. Let's say we turn it, and now there's water flowing out at a rate of R gallons per hour. Oh, shoot. But now, let's say we've got an endless bottle of water. Truly has no end. And this isn't an endless container. It's only got 100 gallons of water. And it has some unknown concentration, which we're going to call C0 initially. Of what? Of salt. So C0 pounds of salt per gallon. Now, what I'm going to do is I'm going to put a fixed value on the water's concentration. It's going to be 0.4 pounds of salt per gallon. Of course, we could just make this another initial value, but I feel like that'd be too much of a hassle, and then it'd start becoming difficult to imagine what our differential equation solutions would look like. So then, you have 0.4 pounds of salt per gallon, and it's just flowing in as well at a rate R gallons per hour. So the amount of water obviously isn't changing. Let's just draw those salt particles a little bit. The amount of water definitely isn't changing because R gallons per hour flows in, R gallons per hour flows out. But the concentration is changing, right? Because unless this is exactly 0.4, which is what we call the steady state, which we're not going to talk about right now because it's just a straight line, not very interesting. Unless this is the exact same as 0.4, then the concentration will change because in the case that this is more salty, less salty water is flowing out and more salty water is flowing in, and vice versa in the case that this has a higher concentration. But what am I really talking about? Well, let's figure this out. So, the derivative of the concentration as a function of time is really just how much is going in over time subtracted from how much is going out over time. So let's figure that out. How much is going in? Well, the concentration of this stuff is 0.4, and it's going in at a rate of R gallons per hour. So then, minus C out, what does that give us? Well, it's R gallons per hour over 100 gallons. Okay, there we go. So now, gotta itch myself. I'm sorry, guys. So here is essentially our equation. But wait a second, we're missing something. Can you tell what it is? No, 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 no. This equation assumes that the water flowing out has a constant concentration over time. When really, if you think about it, it's going to get more and less salty depending on what the content of this thing are. So we have to multiply it by the concentration over time as well, just to ensure that this is accurate and changing. So then we get C prime of t is 0.4 R minus R over 100 C of t. If you watched the last lecture, which if you didn't, you should go watch it now, you will know that this is a first order linear ODE. All right, so how do we know that actually? Well, all we have to do is rearrange. So you'll remember that it looks like y prime plus y of t times f of t, well, not y of t, it is a function of time, but just makes things look more cluttered, is equal to g of t. Now, let's try that over here. Y is just c of t, and is r is not a variable, sorry. It's just another initial condition. So, all we have to do is rearrange to get c prime of t plus r over 100 c of t equal to 0.4r. Things are going to be really easy since r is not a function of time, it's constant. So now, what's our integration factor over here? Well, it's just going to be e to the integral of this, which is just e to the rt over 100. First of all, let's find the integration factor. So we get, oh, I shouldn't have kept it for so long without a cap, but it's okay, it'll recover soon. So we get e to the integral of mu t dt, so we get e to the rt over 100, or r over 100t. Remember, this is still a constant, or an initial condition. You can just change it around, but it doesn't depend on the time that's passed. So we just get d dt of c of t times e to the r over 100t is equivalent to 0.4r multiplied by e to the r over 100t. Now we just take the integral of both sides. Notice that since this is a constant, we just take it out. So we get 0.4r times e to the r over 100t. Now you could integrate this as is if you're a masochist, but I'm going to make the u substitution minus r over 100t so that we can integrate this quite a bit easier. So then we get du dt is minus r over 100, obviously. So that means all we have to do is divide, and suddenly we get e to the minus u, and then a minus 100 over r right outside, times the 0.4r. I should not have put the decimal place that low. So let's put the dt and du. So then this one should be pretty easy, hopefully. This is just minus e to the, this should just be minus e to the minus u being minus r over 100 t. So we get minus e to the r over 100 t minus 100 over r times 0.4r. So we just get, and this cancels out too, 40 e to the r over 100 t. And then what else do we get? So the thing is, actually, once we integrate, we get a constant. And that constant is related to the initial concentration, but we're not going to take that into consideration as of now. And now all we have on the other side is just what? Where was it? Where is it? Where was it? Aha, okay. So this is just going to be c of t times e to the r over 100. All right, so let's do this. So let's arrange this in standard form. So we get c prime of t plus r over 100 c of t equal to 0.4r. So now let's have the integration constant, which is just going to be the integral of this to the eth power, or e to the power of this. It's going to be r over 100 times t. And now here's the good part. We have to take into consideration this constant that comes from the integration. You'll find more details last time when we talked about the integrating factor. So then what do? We multiply both sides by this, so we get that this, and this is just practice from last time, so you should be able to follow all these steps. So we get this side should just be c of t times our original integration factor. Maybe choosing c was a bad choice, but you know, stupid is as stupid does, Forrest Gump. So we also multiplied this side by the integration factor. So let's not forget that. This is just a constant, so we dispense of it. And what is the rest? Pretty simple, right? E over 100t. All that happens is that we have 0.4r e to the r over 100t, and we come out with a constant of 100 over r actually. So we get 100 over r e to the r over 100t, and then plus c prime. That is the most crucial thing here, because the constants actually matter. We can't just ignore them because they carry these crucial terms along with them. So now, once we try simplifying, we get 40 e to the r over 100t plus 0.4r c prime. Then we have c times c of t e to the r over 100t. Normally, we'd just be able to cancel them out and say, oh, it's constant. But with these additional variables added in, now we can see that it actually does depend on the concentration. So if the initial concentration is 40, boom, bam, everything's done. It's just a steady state like this. But now the exponential comes from the initial condition. So now we get c of t, and I'm going to attempt to get an initial, an explicit form here. We get 40 over c, and I'm dividing by c times e to the r over 100t right now. So plus 0.4r c prime over c e to the r over 100t. So this is a constant. This is another different constant. A plus b 0.4b, and it all is just b times 0.4r over e to the r over 100t. So now, what is the role of the initial concentration? Well, let's figure that kind of thing out, okay? So, oh, right. Gotcha. So, let's say that the initial concentration C naught is 40. Then C of t should just be a constant, right? So that means that our answer is hidden somewhere, that our rate is just C of t is equal to 40 plus, and here's the concentration, C naught minus 40 times or divided by this exponential term. So what does that look like? Well, you could have probably imagined that it would be an exponential graph that gravitated towards the line y, or concentration C, is equal to 40. So if it was above 40, it would be asymptotic. And if it was below 40, it had similar behavior. So then we can think about what a direction field would look like. It would probably look like this, where it gets pretty much stable once we get closer and closer to this thing. So you can essentially see, if it starts from here, it goes like this. If it starts from here, it goes like this. Understood? Understand? All right. So that is not what we are supposed to get to today. I know, pretty long, right? I did not mean to go on that long of a tangent. Hope this would be pretty short, but I think it'll be short in post. Anyway, today we were supposed to learn about exact differential equations. So let's actually get to that now. And this is similar to a technique you'll remember from Calculus 3. So essentially, here's what we are going to do. Let me get the thing out. So we have m, which is a function of x and y, plus n, which is also a function of x and y. times y prime equals 0. This is the most general form any single first order differential equation can take. And only a limited amount of these are actually solvable. But hypothetically, this is going to be solvable exactly with our method if the partial derivative of m over x is equal over y is equal to the partial derivative of n over x. The way I like to think about it is like saying with Leibniz notation, my nix. So now let's actually try solving this. So what we do is we use the potential function, which I'm going to symbolize with phi. Now what does this do? Essentially what it does is it gives us an easy way to calculate this. So first of all, we have to verify that this is true. Once we verify that it is in fact true, then we want some hypothetical phi such that the x partial derivative of phi is equal to m and the y partial derivative of phi is equal to n. So now we put y prime in the differential form, just like so. And then by the multivariable chain rule, we get that this is just d dx of phi of x, and y is just a function of x, which explains why this uses the chain rule. Is that 3 parentheses? Yeah. So then that implies that phi of xy is just equal to some constant, c. And that is our implicit solution. Obviously, we can solve for an explicit one after. So that's the rationale behind things. Now, let's look at an example to see how this works. Oh, and by the way, that's my little guy, Daniel. So, let's see.
Who's Daniel?
He's just a little eyeball that I draw when I want to pay attention to something. Like this guy right over here. Yeah.
When you get distracted in the middle of lecture?
No, I think it's like a way to express my thoughts nicely. So how do we do this? Well, let's look at the example 3x minus x squared plus 2y y prime is equal to 0. So here, this is m of xy, this is n of xy. So m of my nix. So when we take the partial derivative of y, there is no y here, so this is 0. Same way, there is no x here, so this is also 0. Might as well draw Daniel here, just because. So you might notice, wait a second, both of them are 0. So, what does that mean? Well, it doesn't mean anything. Since these are the same, they are both exact. But now we have the partial derivative of x equals m. So, since we just took the derivative with respect to x, then we should integrate with respect to x to get the original function back. Should be pretty easy. So we got the integral of 3x minus x squared dx equal to phi. Obviously, we can just add the plus c over here. So then we get phi is equal to 3 over 2 x squared minus 1 over 3 x cubed. But then, wait a second over here. Since we're integrating with respect to dx, that means that our constant could easily be a function of y. So then taking the derivative of x, this could just vanish like your regular old constant. Remember, we're doing multivariable calculus over here. So that means that we have to consider this being a function of y. So to figure that out, we now have to consider the other formula, phi sub y is equal to n. So then we do this the same way to get the original phi back. But then aren't we just going in circles? Well, no. You'll see what I mean in a moment. Once we integrate this is just 2y. We get this is y squared plus h of x. And here's where the realization hits you. H of x is just this, and h of y is just this. we find them just like that. So that means our full formula is phi equal to 3 over 2x squared minus 1 over 3x cubed plus y squared. But you guys have been bamboozled because notice how this is simply one variable, this is simply a one variable function, and this is simply a one variable function. Wait a second, this is separable, which is much easier as it only takes like 2 steps. So you get x squared minus 3x, turn this into the differential form, dx equals 2y dy. Integrating on both sides, all we get is 1 over 3x cubed minus 3 over 2x squared is equal to y squared plus c. So we got basically the exact same thing with much less effort. And remember, since this is a constant, so these two are literally the exact same. I think I made a sign error over here, but other than that, well, the sign error is nothing. Why? Because minus c, and this is still a constant, so we can make it just c. There we go. So that's how we do exact differential equations. Thank you everybody for watching, and we'll see you in the next one.